afternoon all. But today we'll be looking at addition and subtraction of a matrix, multiplication of a matrix by a scalar, and product of matrices. Okay, so let's move on to addition and subtraction of matrices. Now, for matrices to undergo addition or subtraction, a condition must be met. And what is the condition? Both matrices must have the same dimensions. Or for instance, if matrix A, given as Aij, is to be added with matrix B expressed as Bij, then the sum of these two matrices A and B would give us a new matrix C. Okay, so where C is equal to Cij. So the element in the first matrix A plus the element in the second matrix B would give us the sum, will give us a new matrix called Cij. That is to say, given that matrix A is A11, A12, A13, A21, A22, A23, A31, A32, and A33, and then we have matrix B to be equal to B11, B12, and B13, B21, B22, and B23, B31, B32, and B33. So both matrices can be added together under the condition that matrix A has a dimension of 3 by 3 and matrix B has a dimension of 3 by 3. So A can add up with B to give us a new matrix. We have A11 plus B11, we have A12 plus B12, B32, A33 plus B33. So by the time we sum up this, we would have a new matrix called C, which is equal to C. We have a new matrix called C, which is equal to C11, C12, C13, C21, C22, C23, and C31, C32, and C33, where our C11 equals A11 plus B11, and our C21 equals A21 plus B21, and our C33 equals A33 plus B33. Similarly, if subtraction operation is to be carried out on this matrix, then we can say that matrix A minus B will still give us matrix A11 minus B11, matrix A12 minus B12, matrix A13 minus B13. And matrix A33 minus B33, which could also give us a new matrix C11, C12, and C13 under the condition that C11 is equal to A11 minus B11, C21 is equal to A21 minus B21 rather, and C33 is equal to A33 minus B33. So that is how matrix operation is being carried out on addition. So we are going to look at a typical example. Now, if matrix A is given as and matrix B is given and we are asked to carry out A plus B, I, A minus B, I, B plus A, and IV, B minus A. So if I ask to carry out these operations on this particular matrix, then we will have it as this solution. Before we would start solving, we need to confirm if the dimensions are the same. So looking at matrix A, we have 2 rows and 3 columns, and matrix B we have 2 rows as well and 3 columns. So addition and subtraction operations can be carried out on this matrix. So let us find out what the result will be like. At the first element of A, the first element of B rather, will give us this, which will give us a new element of C. And then if we carry out the same thing all through, we'll have this. Okay, we'll have this, whereby the new matrix C will give us the sum of matrix A and matrix B. So the element of matrix A and matrix B for the first one and the first column will add up to give us 1. Give us 1 and will add up to give us 2. So you discover that we have a new matrix C, which is different from matrix A and matrix B. We have a new matrix C different from matrix A and matrix B. Alright, for the second problem, we have it that A minus B would give us minus 5 minus 6. We have 2 minus 0. So this will give us a new matrix C given as and 2. So maybe we can differentiate this from this by calling this C prime, and then we can call this C prime prime. Okay, where C prime represents the operation for addition and C prime prime represents the operation for subtraction. Up next, we'll look at the properties of addition of matrices. So addition of matrices of the same order is associative and commutative. So using the same examples as before, now solving for B plus A, we'll have 6 plus minus 5 4 1 2. Is that taken? And thereafter, the difference between B and A will give us 6 minus minus 5 1 minus 2. Now let us find out about our solutions here. The sum of A and B is 127412, and this expression equals to B plus A 127412, which signifies that addition operation is commutative. That is, A plus B is equal to B plus A. But what about subtraction? We've solved for A minus B to give us minus 1145 minus 2 minus 1 and 2. Then we solved for B minus A, and we had 11 minus 4 minus 5, 2, 1 and minus 2. We discovered that B minus A is not the same thing as A minus B. Hence, we would say that the subtraction of matrices is not commutative. So in our classwork that we'll see later, would apply that of associativity and the addition inverse of matrices. All right. Up next, we'll look at multiplication of a matrix by a scalar. Okay. Now, let matrix A, whose dimension is given as this, okay, where and K is an element of real numbers. Then the product Ka is the matrix B dimension of m times n, where Bij equals Kaij. Okay, so when a matrix is being multiplied by a scalar, then that scalar will multiply all the elements of the matrix to give us a new matrix B, whose elements are Bij. For instance, given that matrix A is equal to 0, 3, -2, and 1, and a scalar K is equal to 6, then we can say that Ka is equal to 6 all into the element of matrix A. And 6 times 1. Hence, this will give us a new matrix called B, which is equal to 0, 18, -12, and 6. So we'll look at the properties of scalar multiplications. Number 1, we have it that scalar multiplication is commutative. Okay, scalar multiplication is commutative. That secondly, scalar multiplication is distributive. Okay, let us prove. Let's just prove one. Let us prove the distributive properties of scalar multiplication of matrix. Okay, let's prove. To Ka plus Kb. Now, for two matrices A and B to be conformable for multiplication, then the number of columns of the first matrix must be equal to the number of rows of the second matrix. That is to say, if we have matrix A For two matrices to be conformable for multiplication, then the number of column of the first matrix A must be equal to the number of row of the second matrix B. That is to say, for A and B to be conformable for multiplication, then N must be equal to P. Hence, a new matrix will be formed whose dimension will be M by Q. That is, let A be a matrix B31, B32. Okay, then the first thing we need to do is to confirm if these two matrices can actually be multiplied. And to do that, we need to check the dimension of matrix A and check the dimension of matrix B and check the condition that holds for the multiplication of two matrices. So the dimension of matrix A is a 2 by 3 matrix and the dimension of matrix B is a 3 by 2 matrix. So what is the rule? The rule states that if matrix A is an m by n of n by n dimension, and then matrix B is of n, let's say, okay, P by Q, then both of them can multiply to give us matrix C, which is equal to M by Q. That is, the number of column of the matrix A must be equal to the number of row of matrix B. Hence, you will see that the number of column of matrix A is 3 and the number of row of matrix B is 3. Because both of them are the same, then multiplication can be carried out between these two matrices. Hence, we'll have that A times B would now give us A11, A12, A13, B11, sorry, A21, A22, A23 times B11, B12, B21, B22, B31, B32. Hence, the pattern for multiplication follows this way, that you multiply the number of rows by the number of columns. You multiply the number of rows of the first matrix by the number of columns of the second matrix, and then the number of rows of the first matrix by the number of columns of the second matrix. That is why for this multiplication to be carried out, the number of columns in the first matrix must be equal to the number of rows in the second matrix. So AB will give us A11, B11 plus A12, B21 plus A13, B31. That is we have this times this, this times this, and this times this. So it follows this pattern. You go this way and then you come this way. Okay, so we have it as this. Then also we have A11, B12 plus A12, B22 plus A13, B32, sorry, B32. Okay, move on to the second row. So we have A21, B11 plus A22, B21 plus A23, B31. Okay, and also A21, B12 plus A22 B22 plus A23 B32. So we have this, which gives us our new matrix. So up next, we'll look at the properties of matrix multiplication. So matrix multiplication is not always abelian or commutative, as the case may be. That is, it is not in all cases that AB is equal to BA. Okay, so matrix multiplication is not always abelian. Okay, it is not always abelian. Okay, matrix multiplication is not always abelian. Matrix multiplication is not always abelian. So if matrix multiplication is not always abelian, they will say that matrix is anti-commutative. Otherwise, if it is abelian, then AB is equal to BA. Then we say it is abelian. Or it is commutative. So it is not in all cases that the product of two matrices is abelian. That sometimes that the product of two matrices will not be commutative or abelian. All right. Thirdly, if matrix AB is equal to 0, it does not imply that either matrix A is equal to 0 or matrix B is equal to 0. So if the product of two matrices A and B equals 0, it does not imply that either matrix A or matrix B is equal to 0. For instance, let's find out about this. Let matrix A be given as 5 minus 5 minus 2 and 2, and B be given as 3 0 3 0. So these matrices are two non-null matrices. They are two non-zero matrices, but their product, let's find out what their product will look like. So as you can see, we discover that even though matrix A and matrix B are two non-zero matrices, but the product of both matrix A and matrix B, they will give us a zero matrix or a null matrix. Also, we have it that matrix multiplication is associative. That is, so long as the matrices are conformable for multiplication. So matrix multiplication. Also, we have another property which states that the matrix multiplication is distributive over addition, but not over subtraction. So matrix multiplication is distributive over addition. That is to say, matrix A into matrix B plus C will give me the same thing as matrix AB plus matrix AC. Also, we have another property that states that the product of a matrix with an identity matrix will also give us the matrix. That is, matrix A multiplied by an identity matrix is still the same thing as an identity matrix multiplied by A, which is equal to A. Okay, finally, we'll see that the product of two diagonal matrices is abelian. That is, AB is equal to BA, where A and B are diagonal matrices. Okay, where A and B are diagonal matrices. So for instance, given that A is expressed as 4003 and B is equal to 3005, then the product AB would simply be 4 times 3 and 0, 0 and 3 by times 5, which is equal to 12, 0, 0, 15. The same thing implies for matrix B times A. So we have B times A will give us 3, 0, 0, 5, and then B times A will give me 3 times 4 and 5 times 3, which is equal to 12, 0, 0, 15. So we can see that this and this, they are the same. Now, the reason we didn't try to expand it further is because by the time we multiply by 0, it will still be added to that matrix. The transpose of a matrix is the interchanging of rows to column and column to rows. That is, giving matrix A to be equal to A11, A12, A21, A22. Then the transpose of matrix A would be seen as taking the first row to represent the first column A11, A12, and taking the second row to represent the second column A21 and A22. So with this, bearing this at the back of our mind, we'll move on to the properties of a transpose. The properties of a transpose. So for the first one, we have that the transpose of a matrix, the transpose of a matrix is equal to the matrix. The transpose of a matrix is equal to the matrix. Also, we have it that the sum of two matrices, the transpose of the sum of two matrices is equal to the transpose of the first matrix plus the transpose of the second matrix. Is equal to the transpose of the first matrix plus the transpose of the second matrix. Okay. So thirdly, we see that the transpose of the scalar product of a matrix is equal to the scalar product of the transpose of a matrix. So the transpose of the scalar product of a matrix is equal to the scalar product of the transpose of that matrix. That is to say that given matrix A, which is equal to Aij, then Ka be given as K into Aij. Therefore, Ka will be equal to Kaij. So if we take the transpose of this, we'll have it to be Kaij transpose, okay, which is equal to Kaji. Okay, Kaji. So fourthly, given the transpose of the product of two matrices, this is still the same. This is still the same as the product of this times this. So we'll look at these examples. In our next video, we'll look at the examples that relate to the properties of all the matrices that we've seen, the properties of addition, the properties of subtraction, the properties of scalar multiplication of a matrix, the properties of matrix product of another matrix, and that of the transpose of a matrix. So up next, we'll consider the determinant of a matrix. Up next, we'll look at the determinant of a matrix.